We're going to look at today at solving our exponential and our logarithmic equations, and we're going to begin by looking at some exponential functions where you've got an equation along the form of b to the m equals b to the n. This is a property that we have, that b to the m will equal b to the n if and only if, and we use a double arrow to show that, if and only if m equals n. And we kind of talked about this just a little bit in some other lessons, but the idea is if you can get the bases to be the same, then the exponents have to equal. And so we can use this to solve. So we're going to look at solving a few. Let's say we have 5 to the x is equal to 125. When you have an exponential function, if you can solve it this way, it's the easiest way. Well, we can write these to the same base. This is 5 to the x. 125 is 5 cubed. If you can write them to the same base, if the bases are equal, then the exponents have to equal. So x equals 3. If we had 4 to the x equals 32. Well, we want to see, can we write these to the same base? Well, we can't write 32 to base 4. That's what, like we did over here, writing 125 to base 5. But we can write both of these to base 2. 4 is 2 squared, and 32 is 2 to the 5th. Now, when you raise to your power, that actually needed to be 4 is 2 squared raised to the x. I put a 2 there. 32 is 2 to the 5th. Now, when you raise to powers, you multiply the exponent. So this is 2 to the 2x equals 2 to the 5th. If the bases are the same, then the exponents have to equal. And we can solve, so x is equal to 5/2. And you could go back and actually check this. If we tried to raise 4 to the 5/2, we know with fractional exponents, the denominator tells us the root we're taking. So we're taking the square root of 4, which is 2, and then raising it to the 5th power, which would be 32. If we had one that was 3 to the 1 minus x is equal to 1 over 27. And we want to write these to the same base, and it's going to have to be to the smaller number. So if we look at this, 1 over 27 is the same as 1 over 3 cubed. But we want our 3 in the numerator, and so we're wanting the reciprocal of it. Well, to make the reciprocal of it, then we use a negative exponent. So 1 over 3 cubed is the same as 3 to the negative 3. Over here, we still have 3 to the 1 minus x. So now our bases are the same, so that means that our exponents equal. And we could subtract 1 and then divide by negative 1, and so we get that x equals 4. So if we raise 3 to the 1 minus 4, 3 to the negative 3 is 1 over 27. If we looked at 8 to the x plus 3 is equal to 16 to the x minus 1. Well, again, we can't write 16 to base 8, but we can write both of these to base 2. So 8 is 2 cubed raised to the x plus 3. 16 is 2 to the 4th raised to the x minus 2. So this is the same as 2. When you raise to powers, you multiply your exponents. And this would be 2 to the 4 times x minus 2. When the bases are the same, then that means that the exponents have to equal. Well, we would distribute. So 3x plus 9 is equal to 4x minus 8. Subtracting 3x from both sides, we get 9 equals x minus 8, and then adding 8 to both sides, x equals 2 17. Okay, so if we went back and checked it again, we've got 17 plus 3, that would be 8 to the 20th, is equal to 16 to the 17 minus 2, 15. Okay, let's get our calculator and just check that one. All right, we've got our calculator now, so let's just check it. 8 raised to the 20th. Okay, now it equals a huge number. It's that times 10 to the 18. And then 16 raised to the 15th. And we see that we get the same answer. So we do have ways of solving for our exponents if we can get the bases to be the same. Now, let's look at one more like this, and then we're going to look and see what we do when we can't get the bases to be the same. And that's not always possible. But let's look at one more. And let's look at 6 raised to the x minus 3 over 4 equals the square root of 6. Well, we can see the bases are fairly similar, but for 6, the square root of 6, we would write that as 6 to the 1/2. So don't forget your fractional exponents are what you use to write your roots. Your negative exponents are what you use to get reciprocals. Now our bases are the same, so that means our exponents equal. So x minus 3 equals 1/2. Well, we can treat it as a proportion and do the cross product. We can get us a common denominator. We can multiply both sides by that common denominator. And I'm just going to do that. Let's multiply both sides by 4. So we get x minus 3 is equal to 2. So x equals 5. And 5 minus 3 is 2. 2/4 reduces to 1/2. So if you can get your denominators to be the same, then that's the best thing to do. You just then set your exponents equal. But if you can't get your denominators to be the same, then we need to use another method. So that's where we're going to use logarithms. Now we've got some steps in using our logarithms to solve by using logarithms. The first thing we want to do is to isolate the exponential expression. Then we take the log of both sides. We will simplify and then solve. Now, our idea behind this is if two numbers equal, if m equals n, then log base b of m equals log base b of n. And this is another if and only if. So it goes the other way. If you have two logs equal, then that means those numbers equal, as long as the logs were to the same base. So if you have two numbers equal, then their logs will equal. And it doesn't matter which base you choose. So what we're going to do is we're going to choose either base 10. Now, base 10, log base 10, we will always write as just log. If there's no base shown, it's understood to be a 10. Or log base e, we write as the natural log, using the ln. We have a choice. We can do either one, and our calculators have base 10 and base e. There are some problems that we will try to work later on that we must use our natural log. So what I always suggest is, since both of these will work in our problems, except a few, and in some we have to use the natural log. So it will work on all problems. The LOG will work on some problems. So I always use my natural log because I know it's always going to work. We get the same answer either way, and I'll actually show you a problem where we get the same answer doing it either way. So let's say we want to solve this problem. 5 to the x equals 17. We want to solve for our exponent. And I don't know how to do this. Your calculator doesn't do this. So we need a method for doing it. So this is where we'll deal with our logarithms. We have two numbers equal, so we're going to take the log of both sides. So I'm going to say the natural log of 5 to the x, which is the power times the log, is equal to the natural log of 17. We simply took the log of both sides. Well, now I can solve for x. I'll divide both sides by the natural log of 5. Now, in this case, I have to go to my calculator to get my answer, so I'm going to divide the natural log of 17 and we'll have to close the parentheses, divided by the natural log of 5. And we get 1.76. And we're going to round these to 2 decimal places. So we're going to get that x equals 1.76. Now I said I would show you that this works even if we had done the log. If we had done the common log of 17 divided by the common log of 5. So if we had done the common log of 17 divided by the common log of 5, and we get the exact same answer. So you'll get the same answer no matter which log you use, but there's some problems that you have to use the natural log in. So I just get in the habit, I will always use the natural log as we work these problems. Okay, let's look at another problem. We're going to look at several problems using our logarithms, and they get to be kind of fun. So let's say we have 7 raised to the 2x plus 1 is equal to 3 to the x plus 2. Well, these aren't the same bases, and there's no way that we can get them to be the same bases. So what we're going to do is take the log of each side. So this is going to be the natural log of 7 raised to that power. So it's going to be the power times the log. And I put it in parentheses because it's that whole power times my log is equal to the natural log of 3 raised to the x plus 2. So the power times the log. Okay, I need to distribute, and so I would have 2x log 7 plus log 7 is equal to x log 3 plus 2 log 3. Now I need to get everything that has an x on one side, everything that doesn't have an x on the other. So I'm going to subtract x log 3. And then I need to subtract log 7 from both sides. So I have 2x log 7 minus x log 3 is equal to 2 log 3 minus the log of 7. Okay, I need to solve, and so I need to get my x's together, but I can't because these aren't like terms, so I have to factor out the x. And then divide by my coefficient. So x is equal to 2 log 3 minus the log of 7 divided by 2 log 7 minus the log of 3. Now we're going to have to put this into our calculator. And when we do, we have to remember our order of operations say we do the numerator. So since there's more than one term, we'll have to put it in parentheses. We do the denominator. We have to put it in parentheses, and then we'll do the division. So as we put this into our calculator, we have to be sure that we use our oops, that's not going to let me show you that whole thing. We can. Okay. Uh, we're going to put in, and we have to use our parentheses. So let's just clear out what all's there. So we're going to have parentheses 2 natural log of 3. I have to close the parentheses for my log. Mine of 7, excuse me, that should have been a 7. It was a 3. It's log 3, I'm sorry. Okay, so 2 log 3 minus log 7. Close for the log, then close for the numerator, divided by, open parentheses, 2 log 7, close your log, minus log 3. Okay, close the log, close the denominator, and then enter. So if we round this to 2 decimal places, it would be 0.09 or 9 hundredths is what x would be. It would be our 9 hundredths. And you could go back in and check that, actually raising them to the power. All right, let's look at another one. This one is going to be 2 log x. And there's a lot of different techniques that we have to do as we go through. So I'm going to try to cover most of them. May not be exactly all of them, but enough that you will then have an idea when you look at a different problem. Okay, when we look at this one, we already have logs, but we don't have a single log over here. We have a difference of logs over here. So we can't use that property that we were looking at, that if you have 2 logs equal, then the number's equal. But if we go back and we condense this side and write it as a single log, this would be log of x squared, power times the log, divided by 7 is equal to the log of 1/12. I just went back and condensed that side. So it's the difference of 2 logs, so that's the log of a quotient. And then we had a power times the log, so that's the log of a power. So now we have 2 logs equal, therefore our numbers have to equal. So x squared divided by 7 equals 1/12. We can multiply both sides by 7 and get 784. Then take the square root of both sides, and we always do plus or minus 784. So we get that x equals plus or minus 28. Now, one thing we haven't been actually looking at, because we weren't given logs to begin with, but back when we first looked at our property for logs, we said that x had to be a positive number. We can only take logs of positive numbers. We can't take logs of negative numbers. So if we were substituting these back in, the positive 28 would be fine, but the negative 28 would not be fine. So we're going to have to eliminate it. So our only answer is x equals positive 28. So we only have the one answer there, because if we substituted in a negative 28, we wouldn't be able to take the log of it. And you can use your calculator to check that you can't take the log of a negative number. We can only take it of positives. Okay, let's look at this problem. We've got e to the 2x minus 2e to the x minus 3 equals 0. So we've got this nice little equation. Well, you might notice it kind of looks like a quadratic equation. So let's do that substitution technique that we've looked at, and let's let e to the x equal u. So if we squared both sides, when you raise to powers, you multiply, so that would be 2x equals u squared. So this is in the form of a quadratic. If we wanted to substitute, we could do 2u squared minus 2u minus 3 equals 0. Well, we can factor this. Factors of 3 that subtract to be 2, 3 and 1. Signs are different, the larger is negative. Then we set each factor equal to 0, so u equals 3 and u equals negative 1. Then we need to substitute back in because we weren't solving for u, we were solving for x. So e to the x equals 3 and e to the x equals negative 1. Well, we need to solve for our exponent, so what we're going to do is take the log of both sides. And here's where it comes in handy that we're using the natural log. If we did the natural log of e to the x equals the natural log of 3. Now, for the natural log, our base is e, so the base of our log is the same as the base of our number, so this side simply equals the exponent. So we get x equals log 3, and we could go to our calculator. The log of 3 is 1.098, which that would end up being 1.10 to 2 decimal places. So this is why we use the natural log, is because if you have base e, you must use the natural log, and it works out so much better. So I always use the natural log, and therefore when it comes that time, will I notice it? Now over here, there is no number value of x that will give us a negative 1. And if we still took the log of both sides of e to the x, well, right here, we can't take the log of a negative number. So that one doesn't work. So we get x is equal to 1.10. So you may have it where it's in the form of a quadratic, and you go through and solve. Now this one looks pretty long. We've got log base 2 of x minus 6 plus log base 2 of x minus 4 minus log base 2 of x equals 2. Well, I've got some sums and differences of logs, so I could write this as a single log. For the plus, that would be times, so this would be log base 2 of x minus 6 times x minus 4 minus would be divided by x, and that equals 2. Now notice this side wasn't a log, so we can't use that property that if two logs equal, the numbers equal, because this isn't a log. So what we're going to have to do on this is write it back in exponential form. So 2 squared is equal to x minus 6 times x minus 4 over x. Over x. Okay, we need to solve this. So we could multiply both sides by x, so we would get 4x is equal to x minus 6 times x minus 4. Well, this is a quadratic, but it doesn't equal 0, so we're going to have to go ahead and multiply it out. And when we do, we've got x times x is x squared minus 4x minus 6x plus 24. And that would give us x squared minus 10x plus 24 equals 4x. Well, I want it to equal 0 so that I can solve my quadratic, so I'm going to subtract 4x from both sides. That would be minus 14x plus 24. Well, let's factor this. We want factors of 24 that add to be 14. Well, that would be 12 and 2. Signs are the same. They're both negative. Setting each factor equal to 0, we're going to get x is 12 and x is 2. Now, we always need to go back and check it in the original equation. And my original equation, let me just, well, it was this, we've got 12 and 2. So let's go back up and look at our original equation. It was right here. What we've got is x equals 12, x equals 2. If we put a 12 in here, we'll have 12 minus 6 is 6. We can take the log of 6. We can take the log of 2. We can take the log of, 12 minus 4 is 8. And we can take the log of 12. So that one's possible. If we put in a 2, then we're going to have 2 minus 6 is negative 4. We cannot take the log of a negative number. So we're just going to have to mark out x equals 2. X equals 12 is a correct solution. Okay, we've got 2 log x equals log 25. Well, we almost have 2 logs equal. We just have this 2 out here. But if you remember, this is a power times a log, so this was the same as the log of a power. Now we have 2 logs equal, so the numbers have to equal. And taking the square root of both sides, we get x is equal to plus or minus 5. Okay, checking. Positive 5 is okay, but we cannot take the log of a negative number. So we're going to have to mark out negative 5, so x is simply 5. You've got to remember you can only take the logs of positive numbers. Now we can get a negative answer. It's just when we put it back into our original equation, it has to be a positive number. Okay, let's look at one last equation that we're going to solve, and then we're going to look at using this in compound interest formulas. If we have 2 log x minus log of 7 is equal to log of 1/12. Well, let's write this back as a single log. So this would be the log of x squared divided by 7 equals the log of 1/12. 2 logs are equal, so the numbers are equal. So x squared over 7 has to be 1/12. X squared is equal to, multiplying both sides by 7, 784. And if we look at taking the square root of both sides, plus or minus the square root of 784, well, the square root of 784 is 28. And again, it can only be the positive. We can't take the square root of a negative number. All right, let's look at where we would use this in some applications. And we can do this in growth and decay problems, or we can do it in compound interest problems. And The problems basically work out the same way. So we're going to use some compound interest problems to work these in. The first problem we want to look at is how long will it take $1,000 to grow to $3,600 at 8% compounded quarterly? If we have that much money and we need to end up with $3,600, how long do we have to leave it in the investment or in the bank? So what we're going to do is use our compound interest formula. That was the accumulated amount was equal to the principal times 1 plus the rate divided by the number of compoundings per year raised to the number of compoundings per year times time. Well, substituting in what we know how much it's going to be. 3,600. We know we invested $1,000. We have this at 8% compounded quarterly. So what we're trying to do is solve for our exponent. We're wanting to know what t is. Now, since we can do this computation, I would go ahead and do it, although it's not necessary. We can still work it otherwise, but it's not a hard problem to do. And it does turn out exact. If it didn't, then I would leave it in the parentheses and with a 1 plus whatever that was. So this is going to be 1.02 raised to the 4t. Now what we want to do is to get our exponential part by itself. Well, we have some other things. We have this $1,000. So we're going to divide both sides by 1,000. So that gives us 3.6 is equal to 1.02 to the 4t. You want to get these to where you have some quantity being raised to the power. Now we can use our rule. We have two numbers equal, so their logs equal. So the log of 3.6 is equal to 4t times the log of 1.02. We want to solve for t, so we're going to divide both sides by 4 log 1.02. And so we end up with the log of 3.6 is equal to 4 natural log of 1.06. And that's going to be our t. So we go to our calculators. And we would have the natural log of 3.6 divided by, we need parentheses because there's more than one thing, 4 times the natural log of 1.02. Close the parentheses for the log, close the parentheses for the denominator. So it's going to take us 16 2/10 years for our investment to grow to that amount. So t is going to be 16.2 years. So it's just a matter of you're plugging in and then solving for the exponent. Now sometimes what we need to do is instead of solving for the exponent, we need to find, well, what percent? So we have to shop around. So at what interest rate would you need to invest $5,000 to accumulate $9,000 in 4 years compounded daily? Now, daily compounding, we usually use the number 365. Part of that is based upon banks have 5 legal holidays where they're closed, and so they're open for business 360 days of the year. And so we'll use that when we talk about daily. Well, our accumulated amount was 9,000. That was equal to the principal, which was 5,000, times 1 plus, we don't know what r is, divided by the number of compoundings, that was 360, raised to the 360 times 4, because we're going to leave it in there for 4 years. All right, on this one, we can do several things. We can divide both sides by 5,000, and so we would get 9/5 is equal to 1 plus r over 360 raised to the 1,440. Now what we're going to do on this one is, instead of using logarithms, we're going to go back to just some algebra. We don't have to use logarithms because we're not solving for the exponent. If we're not solving for the exponent, then we don't need the logarithms. We're solving for a variable inside. So what we would like to do is to get rid of these parentheses. The only way we can do that is to get rid of our exponent. So what we're going to do is take the 1440 root of both sides. Okay, on this side, as we go to work this, we're just going to have that root. What's going to happen here, since I'm raising it to the same power as the root I'm taking, then we just get what's underneath the radical. So that's going to be 1 plus r over 360. So we want to solve for r, so we'll subtract 1. And then we will multiply both sides by 360. So we're going to have 360 times the 14/40th of 9/5 minus 1 equals r. So if we do that on our calculator, we're going to have 360 parentheses. Ooh, okay, now if you remember on your calculator, to get that root, what we do is we put the root 1440, then we go to math, and we'll pick number 5. And so that's saying that's the root that we're taking of 9/5. Well, you can do that. I would put it in parentheses, 9 divided by 5. That would be fine. Or you can put 1 8/10. So we've got 360 times that root of 9/5 minus 1. And we closed for the radical. So then we have minus 1. And we say enter. So we get 0.146976661. Now this is supposed to be a percent, so we need to move the decimal point over 2 places, and so we end up with 14.7% is what you would need to invest that in to have it increase that amount in 4 years. You're asking it to increase quite a bit in a short period of time, so you have to find a high interest rate. So these are some of the things that you can use logarithms for, the types of problems, but it's problems where you're solving for exponents. And as you go through to solve for those, then you will need logarithms.